Hello, Algebra 2. Starting out Chapter 2 here, we're going to be looking at quadratic functions, and really all through Chapter 2, we're going to be working with quadratics. We're going to start out by transforming them, which is going to be similar and built off of what you learned about transformations in Chapter 1. So here we go. All right, so in Chapter 1, you were looking at linear functions. They were going to be those straight lines there. In Chapter 2, we start looking at quadratic functions. And the shape of a quadratic function we call a parabola. And it's going to be that U shape. It could be opening up or opening down. And another way to graph it, if you ever need, is to use a table. So you take a value for x, you plug it into your function, and you get your y values. And then these become your x and y pairs to graph your function. We're going to graph this function f of x using a table, meaning I'm going to take values for x and plug them in. When you are picking values for x, it's good to pick some negatives, pick 0, pick some positives, and then we'll see where we're at. So I'm going to start with -2. I'm going to plug in that for x. So f of -2, plug this in for x, and what I end up with as my coordinate pair here is -2 for x, and I would end up with 15 when I evaluate that for my y value. Okay, so when I got my points and I graphed them here, I'm seeing that I don't see the other side of my parabola yet. So I'm going to pick a few more values from my graph. It looks like I should maybe keep going to the right and pick x being 3 and 4. When I find those new values, I have a few more points to put on my graph. And now I can see both sides of the parabola and I can finish sketching it. Okay, looking at translations, we're going to do horizontal translations first. Horizontal means that your x values are going to be affected, which is why you see the x value in parentheses being changed. Your book describes it a little different here than what I would. I would say that if you see something with x minus h, that it's going to move to the right h units. If you see something with x plus h, it's going to move to the left h units. Move that way. It's a little counterintuitive. It seems backwards, but that's just the way it is. In vertical translations, your y values or your outputs are being changed, so you'll see something being added on to the end of the whole function. If your k value here is negative, less than 0, it's going to go down. And if it's positive, it's going to go up. So this right here would be a positive k. Okay, here we're going to be graphing some examples. Our parent function is f of x equals x squared, so I've graphed that here. I'm going to do some color coding. So g of x is going to be blue. When I'm looking at this function, I see that -2 on the x, that's going to move this to the right 2 units. And then adding 4 onto the end or to the whole function, that's going to move it up 4 units. So I'm going to be moving this function to the right 2, up 4. So I'm going to put my vertex here now, and then I'll just sketch this. So it looks like this, and this is g of x. Now h of x I'm going to make red. Adding 2 right here to the x values is going to move it to the left 2 units. And subtracting 3 here is going to move it down 3 units. So I'm going to graph this. I'm going to go to the left 2, down 3, put my vertex right there, and then sketch the graph. This table is going to take us through some more transformations. First, reflecting across the y-axis. You can't really see it here because it ends up on itself. But your x values just become their opposite, and in math we do that by making the x values negative. Reflecting across the x-axis is something we're going to see a little bit more of, and that's going to make your y values their opposite, so that's going to make the entire function, or the outputs, its opposite. Stretches and compressions. A horizontal stretch is going to affect your x values, and so you'll see that next to your x value in parentheses. And if your b down here, this is written as a fraction, which is kind of weird, but your b, if that is greater than 1, it's going to be stretched away from the y-axis. And if b is between 1 and 0, it's going to be moved towards your y-axis. Over here with a vertical stretch, that's going to affect your y value, so it's going to affect the outputs of the function, so you won't see it affecting the x in parentheses right there. If a is greater than 1, it's going to stretch it away from the x-axis. It's going to make it look skinnier, but think about those y values being further away from the x-axis. If a is between 0 and 1, it's going to move it towards the y-axis, which will make it look wider. All right, here we're going to do some examples. We're going to start with our parent function f of x again. I've graphed that in purple, but this time I'm being a little more precise, and I've made a table of values over here that match my points here. Looking at function j of x here, I can see that my x values are being multiplied by 3, so I know this is going to be a horizontal change because it's affecting the x values. Go ahead and plug in x values to the function, and we'll start again. When I graph this, I can clearly see that it was in fact a horizontal compression. Now, we're trying to figure out what is the factor that it was compressed by. If you go back and look on the table, this is what we see when we're talking about horizontal stretches and compressions, and we know that b is the factor that it was changed by. Now up here we have just a 3. In order to get that 3, what b would have to be is 1/3. 1 divided by 1/3 is 3. Think of a candy bar. And so this would be the same as f of 3x, which is what we see right there. So we would call this a horizontal compression by a factor of 1/3. That's it right there. And on the graph, hopefully you can see that each point is now about 1/3 the distance from the y-axis. On k of x, the first thing I notice is this negative, which is going to make it reflect across the x-axis. And so I'm just going to, with a dotted line, it's not my final answer, I know that it's reflected, so it's going to open downward. When you graph it, it should look like this. And because this was affecting my outputs, not just my x values, but my y values, I know that this was a vertical compression by a factor of 1/4. And you can see with your points too that they are now 1/4 the distance from the x-axis. So example, here my y value is -4. Now my y value is -1. It's 1/4 the distance away. If we combine all of our transformations into one equation, we end up with this vertex form of a quadratic function. And in this, a is representing your stretch or compression, a is representing your horizontal translation, and k is representing a vertical translation. In this problem, we're going to translate f of x, which I've graphed here, and we're going to use our vertex form that we just learned. So first of all, the vertical compression by a factor of 1/3, that is your a. Translated 2 units right, so it's going to be x minus 2, and 4 units down is going to be -4 on the end of it. To graph this, I first go 2 units right, 4 units down, put my vertex right there, and then because it's vertically compressed, it's going to be wider. I don't need to be real precise right now, I'm just trying to see what this would end up looking like. Also, feel free to graph it on Desmos if you want to double check your work. Similar type of problem here, and I've started by writing my vertex form. My g of x is going to be reflected across the x-axis. That's going to make the whole thing negative. Basically, a is -1. Translated 5 units to the left, so it's going to be x plus 5, and 1 unit up, so it's going to be +1. If I go to graph that, I'm first going to find my vertex, 5 units left, 1 up, and then I know it's going to open downward because of that reflection. In example 5, we're talking about things falling on the moon. We know that the moon has different gravity than on Earth. So the first thing I'm doing to compare these equations is to write out my vertex form. And if I write these functions in vertex form, it ends up looking like this. And I can see that the only thing that's different is my a value. It's also really good here to visualize what's happening. So I graphed these in Desmos. For our first function, the red one is on Earth. And so what this is saying is that after 1 second, on Earth, something would have fallen almost 5 meters. If I plug in 1, it's 4.9 meters to be exact. After 1 second on the moon, it will only have fallen not even 1 meter, 0.8 meters to be exact. So if I'm thinking in real life, what this means is that things on the moon are falling a lot more slowly. And when I'm trying to explain what happened with the graph, we had a vertical compression because we can see these y values are getting closer to our x-axis. Now, how much closer did those get to the x-axis? What is the factor of this vertical compression? To do that, we would take our new a value and divide it by the old a value, and what would happen would be I would get 0.16, and so we had a vertical compression by a factor of 0.16.